When we contemplate the size and the scale of the universe and our place within it, which you're forced to do when you think about the distance scales and the sheer size and age of the universe, then I think it's very natural for us to tend to come to the conclusion that we don't matter at all.
Something strange happens as we near the end of the universe. Imagine for a moment that everything you know about space, time, matter, and energy exists inside a vast container. Picture that container as the totality of all that we call the universe. Now, ask yourself what, if anything, lies beyond the walls of that container. When scientists use the term universe, they mean all of space and time and everything that exists within. According to measurements by the Planck satellite in 2018, the universe is 13.799 plus or minus 0.021 billion years old and has a mass-energy density parameter very close to 1 plus minus 0.002, which implies a flat geometry on large scales. When cosmologists describe the observable universe, they refer to a sphere of radius about 46.5 billion light-years, containing roughly 2 times 10 to the power of 52 kilograms of matter and energy. That sphere defines the boundary of what we can see, but it says nothing about what might lie beyond the cosmic horizon.
We have a thing called the Sloan Digital Sky Survey, which maps the positions of galaxies. So you know how much of the sky you've surveyed and you know how many galaxies you've counted. And then you can spread that across the wider universe. And you get this picture of a vast and possibly infinite universe. We know that the universe, or very strongly suspect that the universe is much bigger than the piece we can see. So we have good reason to think that's the case. Whether it's infinite or not is another question. Can you picture infinity? Well, no one can picture infinity. We say the universe began 13.8 billion years ago. So that's a measurement, because we can measure the speed that all the galaxies are flying away from us, essentially. So you can run time backwards, if you like, to find out when they were all on top of each other. It's quite a simple measurement, and we've done that. So we say the universe began 13.8 billion years ago. But actually, all we know really was the universe was very hot and very dense at that time. And we have some theories that the universe was in existence before that, and perhaps some sort of circumstantial evidence. And that means that actually the universe could have always been there, eternal. When I talk to people sometimes, some people get upset about that. Some people would rather it had a beginning. The idea that it might have been around forever is more frightening somehow than the fact that it began. And it's interesting the way that people's minds work.
Some people imagine that outside our universe is empty nothingness. Others picture another universe with its own laws of physics. Yet others suspect an endless sea of universes, each with different physical constants. In modern cosmology, the simplest view is that beyond our observable patch, the same space-time continues indefinitely, with galaxies and clusters spreading out, separated by ever-increasing distances. In that view, there is no outside in any conventional sense. The universe has no edge. It goes on forever, just as the surface of an infinite plane goes on without an edge, even though any creature living on that plane could only ever explore a finite patch. Another way to see this is to consider the cosmic microwave background, CMB. The CMB temperature is currently 2.72548 plus or minus 0.00057 kelvins, and it pervades every direction. If you imagine moving far enough that the radiation you see cools to, say, 1 Kelvin, you still remain within the universe. You cannot step outside that radiation field because it fills all space. If space is infinite, then there is literally no outside. Even if space curves back in on itself, like the surface of a sphere in 3 dimensions, you still cannot find an edge. In a closed model with positive curvature, the universe might wrap around itself so that traveling in a straight line long enough brings you back to your starting point. In that case, outside has no meaning any more than asking what lies north of the North Pole. The idea that the universe might be spatially infinite comes from combining measurements of the Hubble constant and the curvature parameter. The Hubble constant h to the power of 0 is measured to be about 67.4 plus or minus 0.5 kilometers per second per MPC from Planck data and other sources. That means that for every million parsecs, about 3.26 million light years, objects recede from us 67.4 kilometers per second faster. Extrapolating such expansion backward leads to a hot, dense origin, and forward suggests that regions beyond a certain distance will recede faster than the speed of light, isolating them forever from us. That boundary is the particle horizon. It sits at a co-moving distance of about 46.5 billion light years. Objects beyond that horizon are still part of the universe, but are forever inaccessible to us. If you insist on asking, what's outside everything, a physicist might reply that the question violates the premises of the theory. General relativity describes how matter and energy curve space and time, but does not define anything outside its own domain. The equations have no boundary conditions at an edge of everything. The universe simply is the solution of those equations paired with initial conditions at the Big Bang. Asking what lies beyond is like asking what's north of the North Pole. The map doesn't define any northern territory because the concept itself fails at that point. Still, scientists have proposed extensions to standard cosmology that assign meaning to outside. One is cosmic inflation, an early period of exponential expansion driven by a hypothetical field with energy density about 10 to the power of 110 joules per cubic meter. During inflation, tiny quantum fluctuations stretched to cosmological scales and seeded the structures we see today. In the simplest eternal inflation picture, inflation never ends in some regions of space. Pockets of space exit inflation and become bubble universes with their own laws, separated by inflating regions that expand too fast for bubbles to meet. In that model, our universe is one bubble among perhaps 10 to the power of 100 or more. Outside our bubble lies the inflating false vacuum, expanding by factors of e to the power of 60 or more after our local patch froze out. That false vacuum might have energy density on the order of 10 to the power of 27 eV to the power of 4 in natural units, driving expansion at a rate of about 10 to the power of 37 s to the power of -1 in the inflationary epoch. We cannot observe it because any signal from beyond our bubble world would have to cross an inflating region expanding at superluminal rates relative to us. A different idea arises from string theory. In superstring or M theory models, space can have more than 3 spatial dimensions. The theories often posit 10 or 11 total dimensions, with 6 or 7 extra dimensions compactified on tiny scales, on the order of 10 to the power of -35 meters, the Planck length. In such scenarios, our universe might be a 3-dimensional brane embedded in a higher dimensional bulk. Other branes could float in that bulk, each acting as its own universe. The bulk itself might be infinite or finite, but unbounded. The mathematics of Calabi-Yau manifolds suggest there could be 10 to the power of 500 different ways to compactify the extra dimensions, leading to a landscape of 10 to the power of 500 possible universes. Outside our brain lies the bulk with its own geometry and fields that we can access only indirectly through gravity or possibly through exotic particles that leak into the bulk. There are also proposals that the universe might be a simulation, in which case outside would correspond to the hardware running the simulation. In that view, our physical laws would be emergent from computational rules. Estimates for the computational capacity required to simulate our observable universe suggest an information content of around 10 to the power of 120 bits, based on the Bekenstein bound, applied to the maximum entropy of a spherical region of radius 46.5 billion light-years. If the simulation hypothesis were true, then beyond the simulation's limits might lie ordinary physical reality, perhaps similar to our own, or perhaps radically different, depending on the nature of the hardware and software. We would have no direct means to probe that level except via possible simulation glitches or through theoretical arguments about computational limits. Some thinkers have suggested that outside our universe could be regions of nothing, not space and not time. According to quantum cosmology, nothing might be the absence of classical spacetime, described by a quantum vacuum with zero classical dimensions. In such proposals, space and time are emergent phenomena arising from a more fundamental quantum state. That state could be a wave function over different geometries, with no classical interpretation. Outside our emergent spacetime, there is no place or when. Attempts to describe that quantum pre-geometry use tools like the Wheeler-DeWitt equation, which formally takes the form h times the wave function of the universe equals 0. That equation does not include a time parameter, reflecting the timeless nature of the underlying quantum state. Thus, asking what's outside again fails, because the very notions of location and temporal sequence break down. Even more speculative are approaches in which the universe is cyclic. In ekpyrotic models, our universe results from the collision of branes in a higher dimensional bulk every 10 to the power of 12 to 10 to the power of 15 years, with each collision giving rise to a Big Bang-like event. In those scenarios, outside would be the higher dimensional space in which the branes move. The collisions convert kinetic energy into the hot, dense state we observe as our Big Bang. Numerical simulations of such collisions show that the energy densities can reach up to 10 to the power of 23 joules per cubic meter at the moment of impact, generating conditions similar to those seen in the early universe. Between collisions, the branes coast through the bulk, separated by distances that may range from micrometers to light years, depending on model parameters. Another line of reasoning comes from observational cosmology. Astronomers study the large-scale structure of the universe by surveying galaxies out to redshift z equals 7, corresponding to times less than 0.8 billion years after the Big Bang. Current surveys cover volumes up to 10 gigaparsecs cubed, sampling some 2 million galaxies. They reveal a cosmic web of filaments, knots, and voids, but no sign of a boundary or edge. The Sloan Digital Sky Survey and the Dark Energy Survey show structures consistent with Gaussian random fields predicted by inflation, with a power spectrum amplitude of about 2 times 10 to the power of minus 9 at the pivot scale of 0.05 mpc to the power of minus 1. That agreement gives us confidence that what we can see locally extends much farther, though we can never observe past the last scattering surface at redshift z equals 1100, when the universe was 380,000 years old. If you ask a philosopher rather than a physicist, you might get another answer. Some argue that a true outside cannot exist by definition. If it exists, then by definition, it must be part of the universe. They define the universe as the totality of existence. Anything that exists is, therefore, part of the universe. Something that does not exist cannot be outside because it lacks being. This perspective leads to a semantic problem. Outside the universe is a meaningless phrase, like square circle. Others challenge that by distinguishing between universe as all that is and the multiverse as the collection of possible universes. In that view, our universe is just one element in a set, and outside it lies other elements. But then, one must specify the nature of the set that contains them and the relations among them, which again recasts the problem rather than resolves it. In practical terms, we can imagine testing some of these ideas. We measure the CMB to about 1 part in 10 to the power of 5, mapping fluctuations down to angular scales of 0.1 degrees. We map galaxy distributions to scales of a few megaparsecs. We detect gravitational waves from binary black hole mergers up to redshifts of z equals 1, roughly 7.7 billion years ago. And we hope soon to detect primordial waves generated during inflation, which would give direct evidence about the physics of the inflation field at energy scales around 10 to the power of 16 giga-electron volts. We look for signatures of extra dimensions by testing the inverse square law of gravity down to sub-millimeter scales. Current experiments show no deviation from Newtonian gravity down to 50 micrometers. We search for vacuum decay events that would hint at transitions between different vacuum states. None have been observed, implying that the current vacuum state has a lifetime far exceeding 10 to the power of 10 years. When we reflect on our search for what lies outside, we face the limits of our tools and our own perspective. We build telescopes that probe wavelengths from radio waves stretching kilometers long, down to gamma rays with frequencies above 10 to the power of 20 hertz. We launch probes that travel billions of kilometers, and yet none can cross the boundary of the observable universe. We rely on mathematical models that describe curvature, expansion, and quantum fluctuations, yet those models break down when we approach the Planck scale of 1.6 times 10 to the power of minus 35 meters and 10 to the power of 32 kelvins. At that scale, space and time themselves lose their familiar meaning and merge into a seething quantum foam of transient particles and warped geometries. Our best candidate for a complete description of reality is the theory that unites general relativity and quantum mechanics. Over the last 50 years, physicists have pursued theories of quantum gravity, exploring approaches such as loop quantum gravity, string theory, and causal dynamical triangulations. Loop quantum gravity suggests that space at its smallest scales is discrete, made of tiny loops, each roughly 10 to the power of minus 35 meters across. String theory proposes that fundamental entities are not point particles, but one-dimensional strings vibrating at frequencies near 10 to the power of 43 hertz, with their modes of vibration giving rise to the particles and forces we observe. Causal dynamical triangulations attempt to reconstruct space-time from simple building blocks, assembling them in patterns that at large scales look like our familiar continuum. Each avenue offers clues, but none yet yields a clear image of what lies beyond our cosmic horizon. Consider the case of vacuum energy, or dark energy, which makes up about 68% of the total energy density of the universe. Its measured value, around 6.91 times 10 to the power of minus 27 kilograms per cubic meter, drives the accelerating expansion we observe through Type 1a supernova surveys and baryon acoustic oscillation measurements. If this energy remains constant, then galaxies beyond a certain threshold will recede faster than light and fade from view. That threshold, known as the event horizon, sits at a proper distance of roughly 16 billion light-years today. Beyond it, space does not vanish, but stretches so rapidly that no signal can traverse the gap. In that sense, the outside is a region of space that we can never reach or even observe indirectly. Looking ahead 100 billion years, if the dark energy remains unchanged, the universe will enter a phase where only gravitationally bound structures remain intact. Galaxies like our own Milky Way and its neighbors will merge into single systems. Star formations will decline as interstellar gas is used up. Black holes will evaporate through Hawking radiation on timescales far longer than the current age of the universe. Ultimately, the cosmos will approach a cold, dark state. Yet, even then, the fabric of space will extend beyond our reach, unbroken but empty of matter and radiation, receding into an indifferent void. If instead dark energy evolves over time, perhaps decaying into matter or radiation, then the story changes. Models of quintessence posit a field with energy density that decreases slowly. If its equation of state shifts, the acceleration could slow, and the distant galaxies might eventually recede more slowly, letting their light reach us after trillions of years. In a scenario where dark energy decays fully, the universe might transition back to a matter-dominated phase. In that case, the event horizon would shift outward, bringing previously unreachable regions back into view. Yet, even with that alteration, the concept of outside remains elusive. Space still extends without boundary, and we simply sample different volumes at different times. We can also examine the notion of a multiverse more closely. Inflationary theory suggests that the universe underwent rapid expansion by a factor of at least 10 to the power of 26, within less than 10 to the power of minus 32 seconds. In some models, inflation continues eternally in regions that never complete their phase transition. Each pocket that does not exit inflation undergoes its own hot Big Bang, cools, and forms structures. If we take these models seriously, there could be on the order of 10 to the power of 1,000 distinct bubble universes, each with physical constants drawn from a probability distribution shaped by the underlying theory. Our own bubble, with its fine-tuned values like the gravitational constant g equals 6.674 times 10 to the power of minus 11 meters cubed per kilogram to the power of minus 1 s to the power of minus 2, and the cosmological constant 1.11 times 10 to the power of minus 52 meters to the power of minus 2, may be a rare occurrence, or one among many similar domains. Outside our bubble lies an interstitial space that constantly inflates, but its scale is far larger than anything we could meaningfully characterize. Experimental efforts to detect signs of other bubbles focus on searching for anisotropies in the cosmic microwave background. A collision between our bubble and another could leave circular patterns or temperature discontinuities of order T by T equals 10 to the power of minus 5. To date, analyses of full-sky CMB maps from satellites like Planck and WMAP have not uncovered convincing evidence of such features. That absence constrains the probability of nearby bubble collisions to less than about 1 per 10 to the power of 5 gigaparsecs cubed. But those limits still allow collisions at scales we cannot detect, and they do not rule out a vast multiverse that lies just out of our reach. The idea of extra dimensions also reshapes our sense of what constitutes outside. In the brain world scenario, our familiar 3 dimensions are embedded in a higher dimensional bulk. Gravity may leak into the extra dimensions, which could explain why it appears so much weaker than the other forces. Experiments at the Large Hadron Collider have searched for signs of miniature black holes or missing energy that would hint at gravitons escaping into extra dimensions. So far, no deviations from standard model predictions have been observed up to energies of about 14 tera-electron volts. That pushes down extra-dimensional sizes, down to less than 10 to the power of minus 19 meters. But even if those dimensions are compact and tiny, the bulk they produce could extend infinitely in directions we cannot perceive. In that bulk, other brains might carry out alternate universes, and outside our brain lies a realm where gravity flows differently, and particles beyond our detectors roam freely. So, what are your thoughts on this topic? Do you believe that our universe is one of many universes? Share your thoughts in the comments below, and subscribe to our channel for more content.